Hi everyone. Today we're going to study definition of function by rule form and set form respectively. Let's begin with definition of function by a rule form. A function f from a to b is a rule that associates each member of first set A with only one member of B. The first set is called the domain, and the set of all corresponding elements in the second set is called the range. Let us have an example. Here we have a table. This column is for the domain with elements -2, -1, 0, 1, 2. And for this column is the range, and the rule is to take the cube of each element from the domain. So we have the numbers -8, -1, 0, 1, 8 respectively. In here the domain are the numbers -2, -1, 0, 1, 2. And the range, the elements are -8, -1, 0, 1, 8. This is a function because for each domain value there corresponds exactly one range value. This is our final answer. Let us have example 2. Given this table 2, the domain is here with elements -2, -1, 0, 1, and 2. For the range, the rule is to get the square of each element of the domain. So the elements for the range are 4, 1, 0 respectively. It means if I square -2, it will go to the +4. -1 square will be +1. 0 square is 0. 1 square is +1. 2 square is +4. The domain here is the set -2, -1, 0, 1, and 2. And for the range, the elements are 4, 1, 0. This is a function because for each domain value there corresponds exactly one range value. This is our final answer. Let's have example 3. We have this table 3. The domain is here with elements 0, 1, 4, 9. For this column is our range, and the rule is taking square root of each element of the domain. So let us take the square root of the elements of domain one by one. Square root of 0 will be 0. Square root of 1 is 1 and -1. Square root of 4 is 2 and -2. Square root of 9 is 3 and -3. In here the domain is the set 0, 1, 4, and 9. For the range, the elements are 0, 1, -1, 2, -2, 3, and -3. This is not a function because for at least one domain value, there corresponds more than one range value. This is our final answer. Let's go now to the definition of function by set form. A function is a set of ordered pairs with the property that no two ordered pairs have the same first component and different second components. The set of all first components in a function is called the domain of the function, and the set of all second components is called the range. Let's have an example. This is set A, whose elements are the ordered pairs 1, 4, 2, 3, 3, 2, 4, 3, and 5, 4. This is a function because no two ordered pairs have the same first component and different second component. The domain is the set of first components, and the elements are 1, 2, 3, 4, and 5. While the range is the set of the second components, and the elements are 2, 3, and 4. This is our final answer. Let's have example 2. We have here set B. The ordered pairs are 1, 4, 2, 3, 3, 2, 2, 4, and 1, 5. This is not a function because there are ordered pairs with the same first component and different second components. Example, the 1, 4 and 1, 5. So we will not take the domain and the range anymore. This is our final answer. Hi everyone. Today we're going to study functions, particularly the definition of a function, function notation, functions as defined by equations, and functions as defined by arrow diagrams. First, let us define relation. A relation is a set of ordered pairs. I hope you still remember that ordered pairs are those numbers of the form xy. Here is an example. I have here a set of ordered pairs. The first is 1, 2, second 2, 4, third 3, 6, the fourth is 4, 8, the last is 5, 10. The set of the first components of each ordered pair is called the domain of the relation. In here, the domain is 1, 2, 3, 4, 5. The set of the second components of each ordered pair is called the range of the relation. In here, the range is 2, 4, 6, 8, and 10. We may say that the domain is the group of x values, while the range is the group of y values. Now let us define a function. A function f is a relation that assigns a single value in the range to each value in the domain. In other words, no x values are used more than once. In our example a while ago, this is a function because no x value is used more than once. In here, we're going to use images to define a function. I have here 3 sets of images. In the first image A, this relationship is a function because each input is associated with a single output. Note that input Q and R both give output N. For the second relation B, this relationship is also a function. In this case, each input is associated with a single output. In the third image C, this relationship is not a function because input Q is associated with 2 different outputs. Further, a function is a relation in which each possible input value leads to exactly one output value. We say the output is a function of the input. The input values make up the domain, and the output values make up the range. We can think of a function as a machine. We will input an x and we expect an output y, or we say f of x. An example is here. Our function is x squared. When we input a value x, which is 3, it will come inside the function and the output will be the value 9, and that is the value of y. Let's go now to function notation. The notation y equals f of x defines a function named f. Read as y is a function of x. The letter x represents the input value or the independent variable. The letter y or f of x represents the output value or the dependent variable. The letters f, g, and h are often used to represent functions. We will see f of x, as we see in our example here, or g of x, or h of x. Let's go now to functions defined by equations. When you are given an equation and a specific value for x, there should only be one corresponding y value for that x value. Let's have example 1. The equation y equals x plus 1. We're going to substitute any x value in the equation, and one corresponding y value will come. As an example, we say x equals 7. The corresponding y value is 8 only. So we say that this is a function. Let's have example 2. Y equals x squared minus 1. We will substitute again any x value in the equation, and one corresponding y value will come. Suppose we put x equals 2. The corresponding y value is 3. There is no other value other than 3 will come. And we say this is a function. Example 3, y squared equals x plus 5. We will substitute any x value in the equation, and two corresponding y values will come. Suppose we put x equals negative 1. The corresponding y values are 2 and negative 2. This is not a function because, as a rule, there should only be one corresponding y value for that x value. Let's go now to functions defined by arrow diagrams. Let us have an example on how functions are defined by arrow diagrams. Let x equals 1, 2, 3 and y equals the set A, B, C, D. If the arrow diagram on the right, it's here, defines a function f, then let us answer some questions. Letter A, what is the domain of f? B, what is the codomain of f? Letter C, what is f of 3? Letter D, what is the range of f? Letter E, what is the pre-image of D? Letter F, what is the pre-image of A? Looking at our figure here, let us answer letter A. What is the domain of f? The answer is, the domain is x equals 1, 2, 3. Let's have letter B. What is the codomain of f? The codomain is the set Y. The second set, whose elements are A, B, C, and D. Let's have question C. What is f of 3? The f of 3 is C. And that is our answer here. Let's have question D. What is the range of f? The range is the set C, D. Question E. What is the pre-image of D? The D is here. The pre-image is 1. Question F. What is the pre-image of A? The A is here, so A has no pre-image. Hi everyone. Today we're going to study types of functions. Let's begin with the first one. The first is one-to-one function, or sometimes called injective function. An injective function or a one-to-one function is a function f from group A to group B, with the following property. For every element B in the codomain group B, there is maximum one element A in the domain group A such that f of A equals B. For an injective function, f of A equals f of B, and that means A equals B. Let us have some illustrations. I have here two functions. Let's see function f. This is group A and this is group B. This function is one-to-one because each f value that is used only once. It means each used element in group B is used once only. Let's see function G. We have also group A and group B. This function is not one-to-one because in group B, the value 4 is used more than once. The second type is onto function, or sometimes called surjective function. A surjective function or an onto function is a function f from group A to group B with the following property. For every element B in the codomain group B, there is at least one element A in the domain group A such that f of A equals B. For a surjective function, the range and codomain are the same. Let's have two functions also as an examples. The first function is onto because all elements of group B are used. In the second function, this is not onto because look at group B. There is one element which is 6 that is not used. Again, this is not an onto function. The next is bijection or bijective function. A bijective function is a function f from group A to group B that is both injective and surjective. For every element B in the codomain B, there is exactly one element A in the domain group A such that f of A equals B. For illustrations, I have here again two functions. The first function is one-to-one because each element used in group B is used only once. Also, the function is onto because all elements in group B are used. Since this function is both one-to-one and onto, we say this function is a bijection. For the second example, this function is one-to-one because each used element of group B is used only once. But this is not an onto function because the number 6 is not used. Since this is one-to-one but not onto, this function is not bijection because, as per the rule, a bijective function must be both injective and surjective, or we say it must be both one-to-one and onto. Let us see more examples. Check whether the arrow diagram defines one-to-one, onto, and bijective function. Look at the figure here. First, let us check if this is one-to-one. And we say no, because the element W in group B is used twice. Next, is the function onto? The answer is no, because the element Y in group B is not used. Is the function bijective? The answer is no, because the function must be one-to-one and onto. This is our final answer. Let's have example 2. Look at this figure and we will check if this is one-to-one, onto, or bijective. Is the function one-to-one? The answer is no, because the element 1 in group B is used twice. Next question. Is the function onto? The answer is yes, because all elements in B are used. Next, is the function bijective? The answer is no, because the function is onto but not one-to-one. This is our final answer. Let's have example 3. Look at this figure. The first question is the function one-to-one? The answer is yes, because each used element in group B, in the second group, is used once only. Next question, is the function onto? The answer is no, because there is an element S in the second group that is not used. Third question, is the function bijective? The answer is no, because the function is one-to-one but not onto. This is our final answer. Let's have example 4. Look at the figure. Is the function one-to-one? The answer is yes, because each used element in group B is used once only. Next question, is the function onto? The answer is yes, because all elements of B are used. Or we can say the range and the codomain are the same. Next question, is the function bijective? The answer is yes, because the function is both one-to-one and onto. This is our final answer. Hi everyone. Today we're going to study function. In particular, we will study vertical line test and horizontal line tests. Let's begin with vertical line test for a function. The vertical line test can be used to determine whether a graph represents a function. As a rule, an equation defines a function if each vertical line in the rectangular coordinate system passes through at most one point on the graph of the equation. Thus, if any vertical line passes through two or more points on the graph of an equation, then the equation does not define a function. Let us see some examples. This is example 1. Use vertical line test to check whether the graph represents a function. This is the graph. Let us draw a vertical line anywhere on the graph. So we have one vertical line here, and we can see that it touches the graph at one point. The vertical line test says if each vertical line in the rectangular coordinate system passes through at most one point on the graph, it means the graph represents a function. Since this vertical line touches the graph at one point here, we say that this graph represents a function. This is our final answer. Example 2, we have a parabola that opens to the right. Then let us draw a vertical line anywhere on the graph. So we have one vertical line here, and we can see that the line touches the graph in 2 points. And the vertical line test says the vertical line must touch the graph in at most 1 point. So we say that this graph does not define a function. This is our final answer. Example 3 is an ellipse, and we draw one vertical line here that we can see that this line touches the ellipse in 2 points, and because of that we will say that this graph does not define a function. This is our final answer. Let's go now to horizontal line test for a one-to-one function. Once we have determined that a graph defines a function, an easy way to determine if it is a one-to-one function is to use the horizontal line test. This is the rule. An equation defines a one-to-one function if each horizontal line in the rectangular coordinate system passes through at most one point on the graph of the equation. Thus, if any horizontal line passes through two or more points on the graph of an equation, then the equation does not define a one-to-one function. Let us see some examples. Example 1. Use horizontal line test to check whether the graph represents a one-to-one function. This is the graph, an inclined line. So let us draw now a horizontal line anywhere on the graph. So we have this horizontal line here, and we can see that it intersects the given line at one point. The horizontal line test says that each horizontal line in the rectangular coordinate system must pass through at most one point on the graph. And since the horizontal line touches the given line at only one point, we say that this line is a one-to-one function. This is our final answer. Let's have example 2. Again, let us use horizontal line test to check whether this graph represents a one-to-one function. Let us draw a horizontal line anywhere on the graph. So this is the horizontal line, and we can see that it touches the graph in 3 points. But horizontal line test says that any horizontal line must touch the graph in at most 1 point. But since this horizontal line in particular touches the graph in 3 points, we say that the given graph here is not a one-to-one function. This is our final answer. Let us have example 3, a circle. Let us draw a horizontal line, and we can see that this horizontal line touches the circle in 2 points. And we know already the horizontal line test, so we can say that a circle does not represent a one-to-one function. Also, we can say that the circle is not a function itself, by virtue of the vertical line test that it touches the circle in 2 points. So we say that the circle is not a function itself. This is our final answer. Hi everyone. Today we're going to study how to find the domain of the function. So this is finding domains of functions. Letter A. If function written in an equation form, this is what we will do. First, identify the input values. Second, identify any restrictions on the input and exclude those values from the domain. And last, write the domain in interval form if possible. Let's have example. Find the domain of f of x equals 2x squared plus 5x minus 3. The question here is, what are the numbers that we can substitute for x? We can think of many numbers. One example is 0. We can use 0 to replace the x in the function. If we do that, the value f of x will be negative 3. We can think of other numbers like 1 or negative 10 or 50 or 100. We can think of many numbers that can replace the x. If you notice, our function here is a polynomial function, and the domain of the polynomial function is all real numbers. So it means the domain here is all real numbers, and in symbol we can use R, or in interval notation this is equivalent to negative infinity, comma, infinity. This is the interval notation for all real numbers. This is our final answer. Let's have letter B. A function written in an equation form that includes a fraction. This is what we will do. Identify the input values. Identify any restrictions on the input. If there is a denominator in the function's formula, set the denominator equal to 0 and solve for x. Last, write the domain in interval form, making sure to exclude any restricted values from the domain. Let's have example. Find the domain of f of x equals the fraction where numerator is 5 minus 2m all over the denominator m squared minus 9. Actually, we can think of all real numbers as the domain of this function. However, since we know that the denominator should not be equal to 0, our goal now is to find the value of m when the denominator is 0, then exclude in the domain. So what we'll do, we will write the denominator here, and then we will equate this into 0. After that, we will solve for m. So our equation here is m squared minus 9 equals 0. We will use factoring to find the value of m. This m squared minus 9 is factored out into m plus 3 times m minus 3. And then each factor we will equate to 0. So the m plus 3 equals 0. The second factor, m minus 3, is also equal to 0. Then we will solve for m respectively. So in here, the positive 3 we will transpose. On the right side, we will have m equals negative 3. On the other factor, m minus 3 equals 0. Transposing this negative 3 on the right side, we have m equals positive 3. So we have now two values for m. The first is negative 3. The second is positive 3. Again, we look for these values of m because these values will make the denominator equal to 0, and we will make sure that we will exclude these values in the domain. So in writing the domain, we will write all real numbers except 3 and negative 3. In symbol, we can write like this: R to represent all real numbers, then minus the values 3, comma, negative 3 inside brackets. This is our final answer. Let's have this type if function written in an equation form including an even root. It means we have a radical with an even numbered index. So we will first identify the input values. Next, since there is an even root, exclude any real numbers that result in a negative number in the radicand. Set the radicand greater than or equal to 0 and solve for x. The solution or solutions are the domain of the function. If possible, write the answer in interval form. Let's have example. Find the domain of f of x equals the square root of the quantity 7 minus x. Please note that for radicals with even root or index, radicand cannot be a negative value. Radicand means those terms inside the radical symbol. And in here, in our problem, the index is 2. So what we'll do now is to copy the radicand, that is the 7 minus x, and then we will write greater or equal to 0, because we say that this radicand cannot be equal to 0. So we will always use the symbol greater than or equal. And from here, we will solve for x. We want this x to be alone. We're going to remove the 7 here. So we will add a negative 7 to both sides of the inequality. So we have here plus negative 7, and on the right side also plus negative 7. And this 7 plus negative 7 will cancel each other. We will have now negative x greater than or equal to negative 7. We want the x to be positive, so we're going to multiply the inequality by negative 1. We know the rule for inequality that when we multiply by a negative number, the inequality sign reverses. So it will be positive x now less than or equal to positive 7. Now, just to illustrate, we're going to put this in the number line. So here is the positive 7. So x less than or equal to positive 7. It means those numbers on the left side of this positive 7. So this is our graph. And we put a solid dot on top of 7 because of the less than or equal sign. It means the number 7 itself is part of the solution. So for the domain, we will write negative infinity. Of course, we use a parenthesis here, comma. The endpoint is the positive 7, and we use the square bracket to denote that 7 is part of the solution. This is our final answer. Hi everyone. In this video, we're going to learn how to evaluate functions. Let us have example 1. Given the function f of s equals 2s plus 3, let us evaluate a. f of 2. Letter b. f of 2 plus h. Letter c. Fraction whose numerator is the difference of f of 2 plus h minus f of 2 all over h. Letter d. another fraction whose numerator is the difference of f of s minus f of a all over s minus a. Let's begin with letter A. Let us evaluate f of 2. To evaluate f of 2, we are going to copy again the given function. We will write here, but instead of s, we will substitute the value that is written here, which is number 2. So we have now 2s now becomes 2 times 2 plus 3. And then from here, let us simplify further. 2 multiplied to 2 will be 4 plus 3. And 4 plus 3 equals 7. Therefore, the f of 2 equals 7. So we will write the answer here. Then we will proceed with letter B. The f of 2 plus h. The same idea. I am going to copy the same function. I will write here, but for the s, I am going to substitute the value 2 plus h. So we have now 2 times the quantity 2 plus h. Then plus 3. Simplifying this, we have now 2 times 2 will be 4, and 2 times h is 2h, then plus 3. We will now add together 4 and 3. It becomes 7. So our final answer here is 2h plus 7. Then we simply copy this answer in here. Then let's go to letter C. Let us simplify the fraction. The numerator is f of 2 plus h minus f of 2 all over h. I hope you notice that the first function here is our function b. And the second function f of 2 is our first function a. And all over the h. So just to show, we will do like this. For the f of 2 plus h, we will consider again that same function. We will copy here, but instead of the s, I will put the 2 plus h. So we have here 2 times the quantity 2 plus h, then plus 3. This is for the f of 2 plus h. Then minus the f of 2. The same idea. I will copy this function in here, and then for every s that I see, I will change by the number 2. So we have here 2 times 2 plus 3. Then all over the h. Actually, we solved this already, and this is the answer, letter B. And the second function, we have the answer already in problem A. We can simply substitute the values of A and B respectively. So we have now the group 2h plus 7 minus the 7 all over h. And to simplify further, if I remove the grouping symbol, the positive 7 and the negative 7 here will cancel each other. It becomes 0. So on the next line, we can put here 2h all over h. And the h in the numerator and in the denominator can be cancelled out. So we have now our final answer to be 2. And we can write this answer opposite letter C here. Then let's go to problem D. The fraction is f of s minus f of a all over s minus a. The f of s is the original problem, so we can copy it here, the 2s plus 3. Then minus, the f of a is this function, but instead of the s, I will copy the a. So you see here, 2a plus 3. Then all over, same denominator, s minus a. Let us simplify further. Let us remove the grouping symbols respectively. In the first group, we can directly remove the grouping symbol. But for the second group, if we remove the grouping symbol, we need to change the sign of all the terms of the second group. So we have now 2s plus 3 minus 2a minus 3 all over s minus a. Did you notice this is positive 3 and this is negative 3? When we combine together, it becomes 0. So we have now 2s minus 2a all over s minus a. In the numerator, there is a common factor which is 2, and we can factor it out. So the number 2 is factored out, then multiplied by the s minus a. This s minus a has a counterpart in the denominator, which is s minus a also. It means we can cancel the s minus a and the s minus a in the denominator respectively. So the final answer is 2. And we copy this answer opposite this letter D. So we finally completed our answers for example 1. These are our final answers. Let us have example 2. Given the function f of y equals 2y squared plus 5y plus 1. Evaluate this fraction whose numerator is f of y plus h minus the function f of y all over h. Let's begin with the step 1. Let us simplify this function f of y plus h. It means to say, I'm going to copy the same function here, but every time there is y, I will change that value by y plus h. So you see here, we have 2 times the quantity y plus h, and it is squared, plus 5 times the quantity y plus h, plus 1. Then let us simplify this square of binomial. I hope you still remember the special product when we have the square of a plus b. The answer is a squared plus 2ab plus b squared. We will apply this idea in the square of y plus h. So we have here 2 times the quantity y squared plus 2hy plus h squared. Then plus, we'll just copy all the remaining terms in here. Then on the next line, we will multiply the number 2 to each term of the trinomial. Also, this number 5 will be multiplied to the binomial here. So we have 2y squared plus 4hy plus 2 2h squared plus 5y plus 5h plus 1. So we are done with our step 1. This is the value for this f of y plus h. Let us go to step 2, and that is evaluate the given problem here. So this is f of y plus h minus f of y all over h. Let us substitute the values. The first function was evaluated in step 1, and then minus the f of y is the given function here. So we copy it here, then all over the h. We will simplify further. Let us remove the grouping symbols respectively. In the first group, which is a big group, we can directly remove the grouping symbol. While in the second group, it is preceded by a negative sign. We must change all the signs of all the terms of the second group. So we have now 2y squared plus 4hy plus 2h squared plus 5y plus 5h plus 1. Then this negative 2y squared minus 5y minus 1. And then let us see some terms that we can combine. I see here 2y squared, and there is negative 2y squared here. Also this positive 5y, and there is negative 5y here that can cancel each other. There is positive 1 while there is a negative 1 on the last part here. So they can cancel each other respectively. So on the next line, we will simply collect the remaining terms. And the terms are the 4hy plus the 2h squared plus the 5h all over h. In the numerator, there is a common factor which is h that we can factor out. So h is factored out, multiplied by the trinomial 4y plus 2h plus 5. And we can see that there is an h in the numerator with a counterpart h in the denominator, and we can cancel those h. So we have now the final answer, 4y plus 2h plus 5. This is our final answer. I hope you learned something from this video. See you again next time.